Mr. Bell Physics! What the heck is a kilometer? Oh, hi. Didn't see you there. Welcome back to another exciting episode of Mr. Bell Physics. Today, we're going to be talking a little bit about friction. So, in order to talk about friction, we're going to be doing some practical demonstrations as well as some calculations. We're going to start off with the practical demonstrations in the back of the classroom. Why don't you follow me there? Diddly-diddly-doo, 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 diddly-diddly-doo. So what is friction anyway? Friction is a type of force. Now, force is a very broad term in physics and something that applies to many, many, many things. Friction is just one of many of those types of forces. Friction is caused due to the roughness of a surface. Now, you may take a table like the one I'm at right now and kind of move your hands over it, and it feels rather smooth. And that's to be expected, right? It's usually got a polished finish. It's usually made to be nice like that. However, if we think about this on a more microscopic level, not necessarily all the way down to the atom, but down to particles at least, there is some roughness on this table. Now, mind you, it's not that rough. And it's designed to not be that rough. It's designed that we can slide things across it. For example, this weight. We can slide it across a decent distance with a good amount of force. That being said, though, it does stop after a while, right? So if I take this 1 kilogram mass and I slide it, it stops. And the reason why it stops is because of the roughness of the table. Now, the table obviously is not that rough. If I were to instead take a porcelain tile covered in an entire can of Flex Seal like this, and I were to try to have my mass slide across this, as you can see, it's not very effective. Right? It almost stops it immediately. That's because this is a much rougher surface on a microscopic scale than the table is. The measurement of how rough that surface is, or rather how rough that surface interaction is, because it also matters what the mass is made out of, is measured as something called the coefficient of friction. And we'll talk about what that means mathematically on the whiteboard over there in a minute. But the higher the coefficient of friction is, the rougher the surface, the more grip or friction that it has. Now, this is always going to be a number between 0 and 1, usually a decimal. When my seniors earlier this year did a lab, we found that the coefficient of friction of the table was around 0.3. Meanwhile, the coefficient of friction of the tile with rubber on it was about 0.9. So, bigger coefficient of friction, more grip, more friction. Now, friction has many, 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 many real-world applications. And one of them can be found right over there. Wha-cha-cha-cha! Now, what we have here is a Hot Wheels track. Now, this Hot Wheels track is set up for a different demonstration right now, but it works pretty well with this one as well. See, different Hot Wheels cars are built differently. Some of them are able to do this track no problem, like so. Where they go through the loop, over the jump, and off to the other side of the room. Friction applies all over the place here. We are losing energy to heat in the form of friction all the time, both between the actual tire and surface interaction here, but also between the tire center and axle interaction. Which is why if you have ever done a Pinewood Derby car, for example, you're actively usually incentivized to use graphite for your axles, or to at least put a large amount of graphite on your axles to reduce friction. See, we can take a different Hot Wheels car that's built a little bit differently, do the exact same demonstration, the mass is about the same, but it falls short of the jump because it is losing energy to friction that entire time. Now, real world instances of friction apply a lot in physics. Okay? This exact instance is a very good case study of what happens with roller coasters and what needs to be studied with roller coaster design. But understanding both conceptually what's going on, what friction is, but also mathematically and what it actually looks like when we're comparing forces is a very, very important skill. So now we're going to go back over to the whiteboard to actually do some examples to see how we can actually understand what friction really looks like in the real world. Wow! All right, so let's look at some of the actual math here. Now, what we're going to be doing are two introductory level problems for friction, but describing real world scenarios. So, our first problem today reads, a large couch is sitting on the concrete floor of a warehouse. So, for example, you go to an IKEA, you're here to buy a couch, you see one on the floor of the warehouse, you want to move it. The couch has a mass of 150 kilograms. 150. And we're given that the coefficient of friction is 0.5. Now, in order to even start thinking about how to solve this problem, we need to actually look at what the formula is on the board. Now, for force, we're used to working with Newton's second law of motion, which is that force is equal to mass multiplied by acceleration. This is what we're used to right now. Frictional force, however, works a little bit differently. It is still a type of force, and we could plug it back into this equation if I wanted to find how fast something was accelerating due to friction. However, our actual frictional force equation looks like this. Frictional force, which I use this lowercase kind of curvy f, is equal to the coefficient of friction, represented by this Greek letter, multiplied by an object's normal force. Now, if we think back to what we understand about Newton's laws of motion, we remember that normal force is the force that stops us from, say, falling through a chair. Even though gravity is pulling down on us, which according to Newton's first law means that we should be moving, an object at rest stays at rest, object in motion stays in motion unless the force acts on it. Gravity is a force, it is acting on us, it should be pulling us down. We are able to stay at rest because there must be another force canceling it out. The normal force pushing back up on us while we sit on a chair or stand on a table or sit on a couch. The way we calculate normal force is by calculating the force due to gravity and just understanding it's going in the opposite direction. I find it helpful to draw a bit of a diagram to help us visualize this. So let's say we have our couch, which I'm going to represent by that box. The mass is 150 kilograms. I know gravity is pulling it down, force of gravity. But I know that we're on a floor. Actually, no, let me make this way bigger. What am I doing? We have our couch, represented by this box. I know force of gravity is pulling it down. And I know my normal force is pushing back up. The reason why I know this is happening is because my couch is not falling through the floor, and it's also not flying in the air. So I know that these two forces have to be equal in how strong they are, but opposite in which direction they face. Now, in order to calculate the force of gravity, all we gotta do is the mass of the couch, which is 150, multiplied by the acceleration, but due to gravity. Gravity, as a reminder, or weight in general, is the force due to gravity. How much an object weighs in newtons is determined by gravity. So we're really just using Newton's second law up here, except instead of just A, you may see this rewritten as a lowercase g, because we're using acceleration due to gravity here on Earth, which is 9.8 meters per second squared. Doing this number out, 150 times 9.8, I get an answer of 1,470 newtons. So I do that math out, and I get 1,470 newtons. Now, I also need to understand this is pointed down. My acceleration is pointed down. Generally speaking, when we have something vertically speaking pointed down, we call that negative. So this should technically be a negative 9.8, and it should be negative 1,470 newtons. The reason why both myself and a lot of other teachers don't necessarily write that negative all the time is because we already know it's pointed down. We have that in our diagram that it's pointed down. We don't need the sign to also prove that it's pointed down. But when we're doing our calculations, when we need to understand that our normal force is the opposite of gravity, then yes, we need to understand gravity is negative 1470. So therefore, normal force has to be equal but opposite, positive 1,470 newtons. Now I have these forces actually drawn out. Now I know friction is going to be applied here. Okay, it's going to be applied horizontally instead of vertically. I needed normal force though to be able to solve for that. Now I have normal force. It's 1470. If I go back to my given information in this problem, I'm given a mass of 150. So M equals 150 kilograms. And I'm given that my coefficient of friction is a 0.5. Note, coefficient of friction has no units. It is a unitless number. Probably one of our only unitless numbers here in physics. So, now that I have normal force and I have coefficient of friction, I have enough information to plug in and solve for my force of friction. This would be part A on this problem. Part A asks, what would the force of friction be if you tried to push the couch? So, let's figure out that number. Force of friction is equal to coefficient of friction, 0.5, times normal force, 1470. When I do that out, I get that my force of friction is equal to 735 newtons. Now, what does that actually mean? What it means is, let's say I was pushing the box like this, pushing in this direction. Okay, I'm applying force pointed that way. Friction would naturally try to oppose my force. Okay, it is naturally going to apply a force in the opposite direction. Friction always acts in opposition to movement. So, what it means is that I actually have a force applied of 735 newtons right there, going that way. Okay, so that's all well and good. Part B asks, what would the minimum amount of force needed be to move the couch? Now here, this isn't really a math problem. This is a conceptual problem where I have to think a little bit more. If I'm thinking about what's stopping me from moving this couch super easily, the thing that's actually stopping me is friction. So long as I overcome this force of friction, that's 735 newtons, I should be able to move this couch. So the minimum force that I need to overcome is 735. Any force greater than that, I can move this couch. Now, some students ask me, what should I write for this? And that's a good question, okay? I've seen people write it as like greater symbol, okay? Anything greater than 735 works. all I have to do is just write 735. And that's fine by me because they understand that's where the threshold is. I will say, if you're not one of my students, double check with your physics teacher in terms of how they want you to express that. But the reason why I'm okay with allowing a student to just write 735 is because if I apply 735.00000000000000000000001 newtons, I'm still moving the couch. I have no idea how many zeros I just said. But my point is that it can be an infinite number of zeros, so long as there's a 1 at the end, I'm moving this thing. So, in order to convey that information, it's just easier to say, this is the threshold. Right? Anything greater than this moves that couch. So that's cool. Okay? I'm going to erase some of this work to help us with this last part here. So, let's erase this. And sure, we can erase this as well. Okay, we already know what the number is at this point. Part C of this problem reads, if you pushed the couch with 1,000 newtons of force, what would the acceleration of the couch be? So here, I am actually pushing the couch like this. I'm applying a force to it, and specifically that force is equal to 1,000 newtons, like so. Now, my free body diagram here is not done yet. There is still the force of friction. And that's still 735 newtons. Now, I've had a few students already try to just use this 1,000 newtons to figure out acceleration. And that is not correct. Here's why. Acceleration, when I'm dealing with F equals ma, it's Newton's second law, only can be found from the net force acting on an object. Once I figure out all the forces acting on it, total them all up, add them all together, figure out what's left over, that and only that is when I can figure out acceleration. Here, 1,000 newtons is not the only force acting on this. I have 735 newtons acting over here. Now, I have to think for a second, how are these two things related to each other? If they're both going in the same direction, to total them up, I would add them together. But they're not going in the same direction. In fact, they're doing the opposite of that. They're going in opposite directions. So, how do I deal with that? The answer is simple. I take the difference between the two. So, I have 1,000 newtons going to, on my whiteboard here, it looks like to the right. I have 735 going to the left. I want to figure out what my remainder is. So, I do 1,000 minus 735. Mind you, you could do 735 minus 1,000. You'll get the same number. It would just be negative. So, 1,000 minus 735 equals 265. Now, the reason why I like doing it this way rather than the other way is because I don't like dealing with negatives if I don't have to. And plus, I'm not going to be moving in the negative direction. Moving in the negative direction, in this case, would mean moving towards friction, which doesn't really make a whole lot of sense to me. So, I like to keep my numbers positive where possible. So, 265. And I have to recognize this is what is left over of my force. So, this is what I actually am going to use to calculate acceleration. This is net force, so I'm going to use that for acceleration. I'm going to use Newton's second law of motion. F equals m times a. F, in this case, is 265. My net force equals mass, 150 kilograms, times a, which is unknown right now. I should recognize these two numbers down here are being multiplied together. So, in order to undo that, which I want to do to get a by itself, I do the opposite of multiplication, which of course is division. So I divide by 150 to get A by itself. In algebra, anything I do to one side, I must also do to the other side. So I, in fact, divide both sides by 150. 150 divided by 150 is 1, so that just kind of goes away. And I'm left with A equals the answer of 265 divided by 150. When I do that out, 265 divided by 150, I get 1.767 about. Okay. 67! Ha! That's still relevant. I'm still cool, right? So, 1.767. And again, I need my unit here. Meters per second squared. If I don't include my unit, my number means nothing. So it's very important in physics to include that unit. So, final answer for part C, 1.767 meters per second squared. All right, let's do one more problem just to really make sure that we feel good about this. We're doing number 2 on the intro to friction worksheet that I gave you guys. So, number 2 reads, you are pulling a sled filled with snowballs to a snowball fight. The combined mass of the wagon and snowballs is 24 kilograms. You're pulling with a constant force of 12 newtons, and the sled is moving at a constant velocity. Let's start off with a free body diagram, just to kind of visualize what we're working with here. So, we have 24 kilograms here. I know gravity is pulling down. I know normal force is pushing up. And I can calculate those numbers, but we'll come back to it. I'm also told that I'm pulling with a constant force of 12 newtons. But importantly, I am not speeding up. I'm at a constant velocity. Now, for part A, it asks, if the acceleration of the sled is 0, are you pulling the sled with any more force than the bare minimum force needed to make the sled move? And let's think about this for a second. According to Newton's first law of motion, an object in motion stays at that constant velocity unless acted upon by an outside force. There is an outside force acting there, that 12 newtons. But our velocity is constant. Which means that either Newton's first law of motion is wrong, or, more likely, we are missing a force over here. If we are not accelerating at all, remember, F equals ma, which means that if we have any force, we should also have an acceleration. So, no acceleration means that our net force must be 0. If that's the case, we are pushing or pulling rather with 12 newtons. That means friction must be applying 12 newtons of force in the opposite direction. Otherwise, this situation is not possible. That's the tricky part of this problem, figuring that out, that your frictional force isn't explicitly stated in the problem. But through your understanding of Newton's laws of motion, you should be able to somewhat easily figure out that it's actually 12 newtons. Part B asks, what is the coefficient of friction between the sled and the ground? So here, I need to calculate my normal force. I have my force of friction already. I'm finding coefficient. So, let's calculate normal force. To do that, we need gravity, which is going to be 24 times 9.8. That is really ugly handwriting, but oh well. That comes out to 235.2. That is pointed down, which means normal force is the same number pointed up. So, let's go over here and actually do that calculation. Again, my force of friction must be 12 newtons because otherwise I should be accelerating because of my pulling force. So 12 newtons is going to equal 235.2, my normal force, times our coefficient of friction. So let's go ahead and do that out in a calculator. These two things are being multiplied together right now. In order to undo that, we divide both sides by 235.2. Those will cancel out. And just like the last problem, because we do it to one side, we must do it to the other. So now I know my coefficient of friction will equal whatever 12 divided by 235.2 is. Let's see what that comes out to be. Doing that in a calculator, I get 0.051. That is my coefficient of friction. Part C asks, after the snowballs have been unloaded, the sled now has a mass of 2 kilograms. How much force is required to move the sled now? Here, it's important to understand what the coefficient of friction is actually representing. The coefficient of friction has nothing to do with an object's mass or weight. The force of friction does, the normal force does, but not the coefficient itself. See, the coefficient of friction only is a measurement of how rough a surface is. And it is a constant for that surface no matter what. So, I could take the table or the rubber from earlier on in the video and I could put it on the moon and it would have the exact same coefficient of friction. Meaning that here, in order to solve for force of friction with a new mass, which means a new normal force, we can reuse that coefficient of friction that we just solved for. And that's exactly what we're going to do. So, redoing this math now, instead of 24, it's 2. So, 2 times 9.8, okay, because force is equal to mass 2 times acceleration, in this case due to gravity, 9.8, comes out to 19.6 newtons, which means that's also going to be what our normal force is, but again, in a positive direction. So now, I can figure out my force of friction, aka how much force I need to pull this sled with in order to get it to start moving. Force of friction is equal to our coefficient, 0.051, times our normal force, 19.6. In order to find force of friction, we multiply the two together. And I will say I'm going to be using the exact value for coefficient of friction, so your answer may come out a little bit different than mine. What we get is force of friction is equal to 8 zeros, 1 Newton. Now, it should go without saying, there is really no reason to write out all the zeros. This is, realistically speaking, 1 Newton of force. I'm only just doing this just to show off how close to exactly it is to being 1 Newton of force. This is when I say round within reason. This is what I mean. There's no reason to write all this out. Just write 1. So, important things to remember about friction in general. It is dependent on this coefficient of friction here. That coefficient of friction is a unique number for any given surface. Now, I don't care if you're here on Earth. I don't care if you're on the moon. I don't care if you're on the sun. I don't care if you're in deep space. That coefficient of friction does not change. The force of friction, however, does. The reason why it does is because force of friction is dependent on normal force, which is dependent on gravity. Meaning that Earth and the moon, which have two very different gravities, are going to have two very different forces of friction. The last thing I do want to point out, I've been saying coefficient of friction, technically speaking, for any given surface, they have not one, not three, but two coefficients of friction. A static coefficient of friction, which is the coefficient of friction before the object starts moving, and a kinetic coefficient of friction, the coefficient of friction of the object once it already has begun to move. For my class, we generally simplify to just coefficient of friction. The math is still the exact same, but understand that there are going to be some differences there between, okay, is the object moving yet or is it not moving yet? That's the only additional step you need to do in your head to make sure that you're accounting for that. With all that being said, thank you so very much for watching. Make sure to absolutely smash that like button. Make sure to hit subscribe and ring the bell for any notifications. That way you get notified every single time I upload a brand spanking new physics video. And as always, thank you so much for watching, and I will see you in the next video. Have a good one.